Yep. So let me share. Okay, so just let us revisit whatever we learned so far in the last class, and we will quickly start with mini batch. Okay. So basically, the idea is simple. In stochastic gradient descent, in every iteration, what you do, you randomly take out of all the objective functions or different iterations of the objective function, you take randomly any one of them. Okay, that's the idea of stochastic gradient. But in gradient, what you are doing? In gradient, you were calculating the total gradient, and that you were plugging it in your equation. And every time, with a learning rate or step size, the value was keeping on decreasing. Okay, and you were reaching the desired optimum. Okay, so we saw with some Python examples. We saw where it failed. We saw the importance of learning rate also. Hmm? Fine. So here you are seeing like the objective function in this case is usually the average of the loss functions. So what is the loss function again? Loss function we refer to as the training error. Training error in the case of deep learning. That what is the actual prediction? What is should be the actual prediction, and what your model is predicting, they are not the same. So therefore, the difference between them is nothing but the training error or the loss function or the objective function. The same thing. Okay. We say loss function or training error in case of deep learning, whereas in case of optimization, that same thing will be called as objective function. So therefore, you can see that average of the loss functions for each example or sample in the training dataset. So if you take the average of all the loss functions, that's what you are trying to minimize or maximize. Okay, here since it's a loss function, you always try to minimize the loss function. Okay, fine. So therefore, what are we given in this problem statement? We are given the training data set of n samples. So there are n samples. Okay, you can consider n to be 100 or 1000, whatever. So there are 1000 training samples, suppose. So you can see that corresponding to each training data set, there will be a corresponding loss function, isn't it? Corresponding to one sample, there will be a corresponding loss function fix. So this I can go from 1 to so on till which value? Hmm? N. Yes, because there are n such training dataset samples. So each dataset sample has a corresponding loss function fi. Okay. Therefore, how many loss functions can we have corresponding to each sample? F1, F2, so on up to Fn. Okay. Now the objective function we are taking is the average of that. This is exactly what I told here. The objective function is the average of the loss functions of each example or sample. Okay. So therefore, you are taking the summation of each loss function for each sample and you are averaging out. How many such samples are there? N samples are there. Therefore, we are doing 1 by n. Okay. So you can see why the objective function is fx bar is that expression. I hope that is understood. Then what we did, we computed the gradient. Of course, we have to compute the gradient in case of gradient descent. So I am computing the gradient at x bar. So grad f at x bar is the grad of this sum average of the loss functions. So now you think gradient as nothing but the derivative. Gradient is nothing but the derivative. So what you will do? Derivative of the sum is equal to sum of the derivatives. Derivative of the summation is equal to sum of the derivatives. So therefore, you can see when I take the gradient outside and the summation, that is nothing but I can take the gradient inside. I hope that is clear. Hmm? So what we are basically doing here, we are taking the average of the gradient of each sample. You can see this from this statement here. We are taking the average of the gradients of each sample. Okay. So therefore, I told you that what is the time complexity or computational complexity of this problem? You are summing how many samples? N samples. So you have to do n such addition operations. So it is of order n. It is of order n. So therefore, you can see if gradient descent is used, the computational cost is order of n. Okay. Now, when the size of the training dataset sample, small n, keeps on increasing, can you observe that the time complexity keeps on increasing? Order of n. Okay. So as n increases, that is the number of samples, number of training samples, then that means order of n also increases. What is order of n? Order of n is nothing but the computational complexity. Isn't it? Computational complexity. So that increases. That increases. Fine. That increases. So what does it say? That if you have a large training data set, gradient descent is not the way to go. If you want the problem to be solved within short amount of time. Therefore, if you have a deep learning problem which requires lot of training samples, gradient descent is actually not the right candidate, unfortunately. So, but still, but now you should answer like there are GPUs. There are GPUs now. So whatever training samples you have, you give parallel to GPU. That is when you tell that statement, you are coming to mini batch. Okay, when you are trying to parallelize those training samples in GPUs, that is nothing but mini batch. You are dividing the problem into batches. You are dividing the problem into batches. Okay, you can see why this classroom is divided into each batch 1, 2, 3, 4, 5. Okay, simple case, why they need this? Simple case is one bench full, one bench full. But how will you come down? Yes, so that's the case. So you can see that doing batches is something efficient. Fine. So this is the idea, idea where we come through stochastic gradient descent. This is exactly where stochastic gradient descent comes to picture, where we say that stochastic gradient descent reduces the computational cost at each iteration. At each iteration, the stochastic gradient descent reduces the computational cost. How? Observe that Observe that at each iteration, you are computing the gradient. And the gradient involves the summing it up for each training sample. Okay. So when you do that, it is order n for each iteration. Each iteration, it is order n. You can think. Each iteration, it is order n. Okay. So how we can solve this issue? Then researchers came across that why you are taking the summation of all the gradients rather than you can randomly pick the gradient of a particular sample out of those n samples. So instead of the summation of gradient, you can just take the gradient of fi. Okay, that is exactly where stochastic gradient descent comes to picture. And when you do that, when instead of the summation sign, you just, instead of summation, you just replace it with grad fi. If you do that, then what is the time complexity? Order 1. Because instead of summation, which was order n, you are now just computing the gradient of a particular sample, which is just nothing but order 1 formulation. So therefore, at every iteration, it is now time complexity of order 1. Can you now see the simplification? How much time complexity did you save? 1 by n. Now, if your training sample is 10,000, does it matter to you? No. So that's exactly why stochastic gradient descent works very fast as compared to gradient descent. So this is exactly what we discussed last class. Like at each iteration of the stochastic gradient descent, which I'm going to call it as SGD, we can see that we can uniformly sample an index I. An index I means it is a training sample. I means it is a training sample. Okay. And you have the set here at random. At random. So what do you mean by at random we select? Maybe the distribution is uniform distribution. Okay. So usually you will see the Python code I will give. I mention the variance and the mean and the variance, so that the distribution is actually characterized. Okay. Fine. So you can see what happens in stochastic gradient descent. Compute the gradient randomly, random I, for a particular random I from I equals to 1 to n. Compute the gradient grad fi x bar. Okay. For I equals to 1 to steps, depends how many steps you want to take. It's up to you. You do this. X bar is equal to x bar minus eta, the learning rate, times the grad fi of x bar. Can you see the difference? In gradient descent, in stochastic gradient descent, you were using this one. This one was stochastic gradient descent. Sorry, this one was gradient descent. This one was gradient descent. Can you see why this is the case? Grad f is used, but what is grad f? Grad f is nothing but the average of the gradient of each n samples, of all the n samples. But this is gradient descent, but this is stochastic gradient descent. Can you see the difference? Instead of grad f, which required order n complexity, you are replacing it randomly with grad fi. And this grad fi requires order 1 complexity. So you can see why stochastic gradient descent is so computationally powerful. Okay. So therefore, it is meaningful to say stochastic gradient descent is faster than gradient descent. Okay. So therefore, you can see, you might be asked, like stochastic gradient descent, which one is better, stochastic gradient descent or gradient descent? Why? Okay. These can be theoretical questions. Okay. Numerics cannot be framed for these problems because these are mostly computational. So stochastic gradient descent is order 1, you can say, whereas gradient descent is order n. So therefore, as the data set size increases, the training data sample increases in size, therefore order n increases, due to which gradient descent consumes a lot of time. Okay. And in contrast, stochastic gradient descent is just order 1 in process. Therefore, it is independent of the training data set sample set. Okay. Fine. So this is where, and I think we saw one problem here. Um, yes. So here I am doing the same. Like we are taking the objective function. You can see my cursor, x1 square plus 2x2 square. Okay. This is just a two-dimensional function we are trying to optimize. Okay. And you know that 0, 0 is the optimum. Okay. 0, 0 is the optimum. You can check manually why this is the case. So what we do, sorry, what we do, like we add a noise to the gradient. Okay, you can see I'm adding the noise. This is the gradient. Try to see 2x1, 4x2 is the normal gradient. But what were we adding to that? We are adding a random sample over here. It's from randomly you can take from in the interval from 0 to 1. Okay, so we are adding to both of the axes. You can see this is adding noise. This is exactly where you come across stochastic gradient. Okay, fine. So what we do here exactly the same thing. That G1 G2, that is f grad. G1 G2 is f grad x1 x2. So when you substitute x1 x2 here, it will call this function. It will call this function, and when it will call this function, you get this stochasticity involved. Can you see? This is the stochasticity involved here, the randomness, and that is being used in the gradient descent. Hence, it is stochastic gradient descent. Is it okay? Hmm? Why we are adding noise? Yes, that's where the stochasticity comes. That's where the stochasticity comes. So how you can say randomly I can pick one gradient? Basically, you just add the noise. And the noise is just the, I think it is taken from the normal distribution, 0, 1. Okay, fine. Anyway, then I'm trying to iterate it. You can see for I equals to 1 in range steps. Steps I have defined in the previous codes already. So I'm not defining it now. So for those steps, I'm calling SGD, this function. That is, at each iteration, it will perform stochastic gradient descent. Okay, iterative procedure. It is an iterative procedure. Okay. So the way you do it, and you store it in x1, x2. So results, you store it in the list known as results. Results dot append x1, x2. That what it does. Results is an array or a list, whatever matrix, and you are adding x1, x2 every time you are iterating. So finally, if you display the results, if you plot results, it will give you the coordinates of the stochastic gradient, how it goes. Okay, fine. And the other things are just plotting. So you can see this over here, like, um, yes. So you can see this is the stochastic gradient for this. These are, what are these things? Why we are seeing a lot of them? X1 square plus 2x2 square equal to C. You are varying C. X1 square plus x1 square plus 2x2 square equal to C. And you vary C like 1, 5, 7, 10, 20. The more you do it, we saw with one example. The more value you take, it will go like this. This corresponds to each C. Maybe this is 1, 5, 10. This is 20. Okay, that's what you're seeing here. Okay, fine. Okay with all. So we started from this initial condition. We started from this initial condition and we performed stochastic gradient descent with a particular learning rate. Okay, and then you can see that first few iterations are good, but here, as as a contrast to gradient descent, it is not exactly hitting or converging to the optimum. There is a noise around. Can you see it? Can you like see this one? See this near the optimum level 0, 0. How the noise is affecting here. Okay, and I will show you gradient descent. Yes, can you see now how it differs? In gradient descent, it just quickly goes to 0, 0. In gradient descent, it just quickly goes to 0, 0. But in stochastic gradient descent, it oscillates. It oscillates near the optimum. Okay, can you see? Here, you see, we started from here. Then, as we iterate the gradient descent, it went here, then here towards optimum, and very nicely, it settled at 0, 0. This is 0, this is 0. But when we come to stochastic gradient descent, this is the same function we are taking. When you come across stochastic gradient descent, you see the difference. At 0, 0, at 0, 0 here, it is not just converging to 0, 0. Suppose this is 0, 0. Suppose the mic is 0, 0. It, gradient descent was just converging here. But what is stochastic gradient doing? It is oscillating near the optimum. But we cannot say like when it converged, okay? But that is one disadvantage of stochastic gradient. Like it doesn't like you, of course, you got away from the local minimum or local maximum, whatever optimum. But when the true solution comes, when the true optimum is there, it is not just converging there, but rather oscillating near the optimum. Okay, that is one just a minor disadvantage. Okay, so yeah, I think, yeah, this is something like I told you one thing, like you have n training samples, and what we are doing is we are picking one at random. We are picking one training sample at random, and we are doing stochastic gradient at that iteration of that random sample. Okay, of that particular random sample, ith random sample. But like you must have learned in data analytics that you can do a sampling. I think sampling of data sets. Okay, you can do sampling in two ways: sampling with replacement and sampling without replacement. Okay, so which one is better? If you can do both ways, which one would be better? So turns out both are better. Okay, turns out both are better according to the applications you need. Okay, that's what we see. We'll see. You can see that stochastic gradient descent with replacement, you can see the loss function on the y-axis and the number of steps or the epoch. We say the number of training steps as epochs. I hope you must have learned already in predictive. Okay. So this is another way of saying, if you are in numerical methods, you will say how many number of iterations. If you are in predictive analytics or deep learning class, you will say how many epochs. Okay. That's the only difference. Okay. If you are in numerical methods course, you will say how much step size. And if you are in deep learning course, you will say what is the learning rate. Okay, so those are the two different ways. Done. Okay. Okay. So stochastic gradient with and without replacement. With replacement, you can see something in blue dots. So you can see how the loss function varies. How the loss function varies with the number of iterations. Okay, with the number of epochs. I can say that yes, there is no definite situation. I think we cannot compare. But one thing you can say that the loss in stochastic gradient without replacement, which is in orange color, is bit bigger. I hope you can see that. You can see that whatever situation you consider, most of the times the orange curve is above the blue curve. Can you do you agree or no? Yeah, of course, at this point it is not the case. Okay, at this point it is not the case, but most of the other cases you can see that the loss function, the amount of loss in your training data set for your deep learning problem, you can see that without replacement cause more loss. Without replacement, why without replacement caused you more loss? What does it mean without replacement? Without replacement means hmm, exactly. So it might be that you can get the same value twice. Okay. Is it correct? Anyone? What do you do without replacement and with without replacement? Huh. Hmm. Yeah. What happens with replacement? With replacement, you take it and you then again return it. Yes, yes. But yeah, you can see that without replacement, you are facing more loss. With replacement, you are facing less loss. Okay. So this is just one experiment to show you like why this is the case. But as turns out that both are profitable. Both are profitable. We'll see that. Uh, I think here. Yeah, we'll see this. Yeah, compare the convergence of stochastic gradient descent for this data set sample x1 y1 till xn yn. Okay, with replacement and when you sample without replacement. Okay, this is the question actually. This is the question. So how can you compare the convergence of stochastic gradient descent for the two of the cases? So you can see that gradient variance. Of course, when you add stochasticity, the gradient will vary. Okay, when you add stochasticity, the gradient will of course vary. Okay, so with replacement, the gradient variance is higher. Okay, with replacement, the gradient variance is higher. Why? Because there are chances that you take the same sample more than once. Okay, and therefore they can be added in your averaging. Okay, turning out to spike because that can turn away from the mean, right? You can think that suppose the one you are taking out, okay, is of higher gradient, okay, and others are not that higher gradient. Okay, fine. When you again put that back and in the next round you can again take it, so you are adding it twice. Due to that, your gradient value will increase, isn't it? Which was not the case without replacement, right? So therefore, you can see that when, like, you have with replacement, when the same data sample can be chosen more than once, your gradient can vary by a large amount, because lot of data sets can be taken more than once. Yeah, lot of data sets can be taken more than once. Fine. Okay. I hope you agree with that. Can, or you need to think a bit. Try to think. Try to think. So you have training and data samples. Okay. And we are talking about with replacement. Suppose the gradient of this guy turned out to be 100, and the gradient of other guys are, say, 50 or something, around 50, less than 50, all other guys. So since if you take with replacement, suppose you took this in your first trial, gradient is 100 plus. In your second trial, it might be you choose 1, so it is 50, fine. Suppose in your third trial, you again choose the second one, it got 100. It got 100. If it was without replacement, you would never encounter this 100. If it was without replacement, you would never encounter this 100 again. Due to this, with replacement, you are facing this 100 again. That is spiking your summation of gradients, right? Don't you? Is okay. Okay, this is with replacement. With replacement. Without replacement, what should be the scenario? Suppose you took the first trial, that is 2, that is gradient 100 plus. You take 2 again, because that is gone without replacement. You are not going to replace it. So 100 is never going to come back. So whatever other gradient you take, we have assumed that it will be less than 50. So you can see it is 50 or some number which is less than 50. So you can see with replacement, the gradient, final gradient, this sum is greater than this guy. I hope it is clear. Hmm? Who will explain it back? Who will explain it back? Can anyone explain it back? Hmm? Are you getting the concept or no? Maybe Durga can explain. No, no. We are actually understanding the first concept here, gradient variance. Okay, how the gradient can vary, how much the gradient can vary if you do with replacement and without replacement. I am telling that with replacement, the gradient can vary by a higher amount than without replacement. So I am telling the intuition behind this, why that is the case. Why that is the case. With replacement, I told you that suppose the second sample, maybe take the only the second sample. You can think one of the sample will have higher gradient without any problem. Can we assume that? Okay, let us say second sample has gradient 100, other samples may have less than 50. Okay, so second is the most maximum one. Okay, so with replacement, what does it mean? That second sample can be chosen more than once. Is it correct? If it can be chosen more than once, so when you are taking the summation of gradient, can you see that 100 will come multiple times? 100 will come multiple times. Is it okay? Now you understood that. So that will boost the summation of gradients by a large value, because 100 you are summing it up. That will boost the summation of gradient by a large amount. Now you come to without replacement. Now you come to without replacement. Okay. What does it happen without replacement? When you take without replacement, 100 can occur how many times? Hmm? Only once, because you took second sample, and after that you can never take two, because that is already taken care. Okay. So you can see that in the first case, with replacement, the summation of gradient is higher, and without replacement, the summation of gradient is lower. So therefore, replacement, the variance in gradient can be higher. The variance in the so that is important because you finally it depends. Stochastic gradient depends on the gradient of a particular sample. Fine. And if you are taking the second sample again and again, then it is difficult. Okay, then it is difficult. Okay, I hope that is okay. Convergence speed, you can see, like, yeah, due to redundancy, because you can take the same sample more than once, therefore it is slower. Okay, but mind you that when you do without replacement, you are covering the full training sample. Of course, you are covering the full training sample, isn't it? Is it okay? So therefore, this is faster because you are able to cover the full data set. Fine. So this is the third one, independence of update. Yes, it is fully independent, whereas this is not. Okay. Try to think why. Try to think why. Okay. Now comes the main important point. I told you that with replacement and without replacement, which one to choose. The point is, like, it depends on the problem you want to achieve or you are taking care of. If you are working with large data sets, okay, then it's okay. It's okay to have with replacement. Okay, it is okay to work with replacement, mostly in online learning cases. But when you are working without replacement, it is efficient if you are working with these kind of problem, that is mini batch training and finite data sets. Observe that if you have finite data set, as I told you, 3 or 4 data sets, out of that one is higher gradient, 100 or 200, and you are working with replacement, so you are taking 200 multiple times, then it is not a good idea. That will vary your gradient by a higher amount. Okay, is it clear? Hmm? Okay. So you can see that, yeah, this is what I have written just like that. Like, for practical machine learning task, sampling without replacement, that is full pass per epoch. Okay. Without replacement means you are covering the full trainings data sample, full number of all the training samples you are covering, full coverage is generally preferred in machine learning task because it ensures that all data points contribute evenly. Okay. Reducing variance and improving convergence. We don't want higher variance, actually. We don't want higher variance. Higher variance is a problem. Okay, you know why? Because you're iterating at every step, and at every step you go in a smooth update. It should not be varying with a large amount. Okay, it might be that you just get kicked away from that original state and optimum is there and you are there due to large variance. Okay. However, sampling with replacement can be useful in certain cases like bootstrapping methods or streaming data scenarios. This is for you to, like, see or check online, like, why this is the case. So I give these 2 words to you: bootstrapping and streaming data scenarios. Why these can be useful for with replacement, sampling with replacement. So try to explore if you are interested. If okay. So this was all about the gradient descent. Okay. Mhm. Yes. So let us come back. Let us come back to mini batch. Okay. That is all the story about stochastic gradient descent. But you know that stochastic gradient descent has some limitations. What is that limitation? What is the limitation? What is the limitation in stochastic gradient? Anyway, like, if you have lot of training samples, then it is better. Like, people actually thought, like, researchers actually thought that, yes, we got some method which is better than gradient descent. What is that? Stochastic gradient descent. Now researchers thought, can we get something better than stochastic gradient descent? And the answer is positive. Yes, it is mini batch. What is so popular in mini batch? Mini batch gradient descent came to picture when GPU came to picture. Okay, I hope you know about GPUs. I hope you know about GPUs. How GPUs can solve, like, I hope you watch the videos given by NVIDIA. I hope you watch some videos given by NVIDIA, like how they can fastly perform, how they can fastly perform the, how they can fastly perform these operations. Okay, so you know that, like, maybe I can give you one small example. Yeah, we'll take this example. I think this is the most simplest example for you all to understand, those who don't have any exposure to GPU or CPUs anywhere. Anyway, so the idea is matrix multiplication. How you multiply two matrices? That's my question. How you multiply two matrices? How you oh, how you multiply two matrices? Anyone? How you multiply two matrices? So there are particular methods. Like, let me tell you, A and B. Suppose they are of particular order and you are trying to multiply them. This is the matrix. This is the matrix. How you do this? First row, first column. But sadly, this is the slowest process. This is the slowest process you can go through. Okay, this is one method. Second method is, anyone? Like, take these two matrices, take this matrix A as usual, and multiply with only the first column. Multiply this whole matrix A with the first column of matrix B. Okay, what you get? It is okay. It is okay because this is n cross n, and the size of one column is n cross 1. So still you can multiply. Still the matrix rule. This is what you get. This is column wise multiplication. Okay. This is faster than the first. I will show you using Python that it is actually the case. Okay, we will compute the timer in the coding. We will take two matrices A and B, and we compute with first scenario. We will record the time. We'll compute through second scenario. We will record the time. We will see that second scenario is taking 1/10th of the time than the first. Okay, so what you were doing till now is the slowest one. I am also doing it. So there is also a third one. There is also a third one, that is no multiplication, nothing. Fully you multiply. Give it to the computer software. Full blockwise multiplication. Full blockwise multiplication. That is faster than the first two. That is faster than the first two. Okay. So these are the three types of matrix multiplications. Okay. We will see through the timer why this is uh, faster, which one is faster, which one is slower, and all these things. But this is just the beginning of mini batch. This is just a very nice example to start with mini batch. Okay. Anyway, I think these are a lot of theories, but I think that will be something useful to you. Uh, yeah. So